what is the blue area? As you can see here, we've got two semicircles, one inside of the other, and we've got a tangent to the inside semicircle that is basically touching the outside the circumference, as you can see, of the larger semicircle with a length of 6. Now I've highlighted that those lines, that tangent and the base of the largest semicircle, AB, are parallel, so they're going in the same direction. Yeah, they're parallel. Can you find the blue area? Now, I'm going to show you my solution to this problem in a few seconds. So if you want to have a go at this problem yourself, pause the video now. Otherwise, I'm going to show you my solution in 3, 2, 1. Okay, so the first thing I would do with this problem, like with any problem involving circles, is I would start to put some radii on. I'm going to identify the centre of the large semicircle AB as O here with the cross there. So I'm going to put my radii on. Now that radius, I'm going to make it so that it is meeting this tangent at right angles, so is exactly perpendicular to the base of the large semicircle. Now what that means is it will split that length of 6 into 2 3s. It will bisect that chord. Now I'm then going to put my other 2 radii on that join up with either end of that chord. Now I don't know what length they're going to have, but they're going to be the radius of that large semicircle. So let's call that capital R. You'll see why that's capitalized in a second. Because what I'm going to do is I'm going to take this central radius and I'm going to shorten it so that it goes just up to, just touches that chord. What I'm then going to do is I'm going to call that lowercase r, because that will actually be the radius of the blank space semicircle, the white semicircle if you like. Okay, because that is going to go up to the chord which is tangent to the white semicircle and therefore must be the radius of the white semicircle as well. Now from there, what I can do is I can use Pythagoras, because I've got this right angled triangle, so I know that 3 squared plus lowercase r squared is going to equal capital R squared. What I'm then going to do is I'm going to square the 3, and I'm going to rearrange this to get r squared, capital R squared minus lowercase r squared is equal to 9. And I'm going to save that for later because that's going to be important. At the minute, I'm going to need another equation to work out either one of those r's, because you need 2 equations to work out or solve a system with 2 variables in. Now, what I'm then going to do is I'm going to start to work out what the equation would be for the blue area. Now the blue area is going to be a half of pi r squared, capital R squared, minus a half of pi and then lowercase r squared, because both of those things will be the area of a semicircle, pi r squared, and then when you half it. Now I can factorise out a half from both of these things, and I can factorise out the pi. So that is going to give us this, a half pi in brackets capital R squared minus lowercase r squared. And if you haven't already spotted it, I can substitute into this the equation from earlier because I've got that is equal to 9. So I'm going to plug that in and I get the blue area is a half pi times by 9. So the blue area therefore is 9 over 2 pi units squared. It's a pretty neat answer, I think, for this problem where you've got a semicircle that is not centered inside another semicircle, and actually we didn't need to, in this case with our solution, work out what either of those radii were, which is quite interesting. If you were able to solve this problem yourself and you use the same solution or a different solution, let me know down in the comments below. And all that's left to say is thank you very much for watching. If you enjoyed this video, make sure to drop a like on the video, and if you're not already, please subscribe to the channel and check out the video just up here. Thank you, and I'll see you next Monday at 5 PM for another problem solving video. Until then, bye bye.